There is a new report from NASA that shows that 3I Atlas might be picking up a little speed in, quote, non-gravitational acceleration. But what does that mean? Well, basically, it means it's being propelled by some other force besides gravity. Maybe it's thrust from burning off of chemical compounds as it got near the sun, which happens occasionally. It would be natural for comets. They usually burn off some of those chemicals, and that's what you see in that big cloud afterwards. And we would see a very big cloud around it once we get a very good visual soon, but we haven't yet.
At 4:16 Universal Time, a silent blur entered our skies. An interstellar wanderer already breaking the rules written for worlds that orbit our sun. An object from another star system is tearing itself apart faster than scientists predicted, leaving researchers scrambling to understand each unraveling moment. At dawn on the 1st of July 2025, a routine survey frame at Hawaii's Atlas Observatory showed a faint moving streak. Nothing unusual at first, but follow-up calculations revealed an eccentricity of 6.1. No solar system object moves like that. Only something from deep interstellar space does, racing in at 57 kilometers per second, too fast for the sun to hold. The confirmation brought silence. Another interstellar visitor, 3I Atlas. Unlike Oumuamua or Borisov, this one was already active, shedding material long before any heat could wake it. That single fact rewrote expectations. Interstellar objects weren't supposed to behave like this. The deeper astronomers looked, the stranger 3I Atlas became.
3I Atlas was discovered on July 1st by the NASA-funded Atlas survey. It was discovered using their telescope at Rio Hurtado in Chile, and it was first detected as a speck of light moving relative to background stars. We collected a good amount of data, more than 100 observations. We know its trajectory fairly well. We know it came from outside the solar system.
When the first brightness readings arrived, they carried another quiet surprise. Observers measured magnitude 10 to 12, unusually strong for an object still far from the sun. Photometric data from amateur and professional telescopes across the world began to align. 3I Atlas was not just reflecting sunlight. Something inside it was actively releasing material, expanding a faint but measurable dust coma around its nucleus. In ordinary comets, this happens much later, typically closer to the inner solar system, when sunlight begins breaking volatile ices apart. But 3I Atlas brightened early, as if its internal reservoirs were reacting to forces unknown within our system. As days passed, more readings arrived. Light curves revealed irregular flickers, slight rises and falls in brightness that hinted at uneven jets or rotation. Each shift carried meaning. Each data point suggested a structure more fragile than expected. Yet despite these anomalies, most astronomers believed the object was stable. The early dust coma was modest. The activity appeared controlled. Models projected a smooth inward journey. Nothing indicated imminent collapse. The assumption was simple. Whatever forces powered this early outgassing, the nucleus could withstand them. For a moment, the scientific world allowed itself to exhale. The third interstellar visitor seemed complex. Yes, unpredictable perhaps, but intact. But beneath that growing veil of dust, something was already changing. Subtle stresses were building. Jets were carving unseen weaknesses. And the object, shaped by forces born a galaxy away, was preparing to rewrite every projection drawn on Earth. What followed would dismantle the idea that interstellar comets behave like the ones we thought we understood. On the 3rd of October 2025, as 3I Atlas swept past Mars at a distance of nearly 18 million miles, an opportunity opened that astronomers could not afford to miss. The Mars Reconnaissance Orbiter, circling high above the red planet, was uniquely positioned to see what no Earth-based telescope could capture. Its high-rise camera, normally used to study Martian dunes and eroded cliffs, was turned outward, toward a visitor from another star. When the images arrived, they didn't look like any interstellar object previously seen. The nucleus was lost inside a haze of dust, but surrounding it was a structured tail, sharper and more textured than expected at such a distance. Bands of material curled outward, as though shaped by jets erupting from beneath the surface. The brightness was uneven, shifting across the coma like a lantern whose flame refused to stay still. Some frames hinted at possible jets, narrow streams of dust shooting away from the nucleus at slight angles, creating faint asymmetries. These features were subtle, almost hesitant, but unmistakably real. They told a story. The object wasn't simply active. It was active in ways that hinted at internal complexity. For many scientists, this was the turning point. The earlier assumptions of stability began to feel fragile. Comets from our solar system displayed predictable behavior, but 3I Atlas did not. Its tail patterns were too organized, its brightness too inconsistent, its activity too early. Something inside it was shifting, building, straining. And as the MRO images circulated through research teams, a quiet realization spread. This was no ordinary interstellar traveler drifting harmlessly through our system. It was a volatile body under stress, and the closer it came to the sun, the more its secrets would be forced into the open.
So combining the data from Lucy, Psyche, and Earth-based telescopes, scientists are hoping to better understand both the three-dimensional structure of the comet and the nature of the dust.
After the Mars flyby, the scientific response expanded into a coordinated global effort. No single observatory could track the complexity of an interstellar comet behaving outside known models. And so, in a rare alignment, instruments across the solar system turned their attention toward 3I Atlas. NASA's stereo spacecraft tracked the evolving plasma tail, watching as solar winds sculpted it into longer, sharper forms. Subtle kinks and folds appeared, signatures of turbulent interaction with charged particles. These were clues, early hints that the object was shedding more material than expected. Meanwhile, MAVEN, orbiting Mars, made a striking detection in the ultraviolet spectrum. Hydrogen emissions rising from the comet. Hydrogen often marks the breakdown of water or other volatiles. But MAVEN observed more than predicted, suggesting deeper or more reactive reservoirs inside the nucleus. The SOHO spacecraft, stationed near the Sun, monitored the brightness curve as 3I Atlas moved inward. Every reading pointed in the same direction. The comet was brightening faster than any model had projected. More dust, more gas, more instability. NASA's PUNCH mission mapped the flow of particles around the comet, connecting tail disturbances to rising activity. Yet even with these assets, gaps remained. That's where ESA's ground telescope stepped in, providing high-cadence optical measurements that added texture to the narrative. The tail was becoming longer and more structured, almost architectural in its layering. This coalition of instruments wasn't a luxury, it was a necessity. Each wavelength revealed something the others could not. Only by layering ultraviolet, optical, and plasma data together could researchers begin to understand what they were seeing. But for all the precision of this interplanetary surveillance, the pattern that emerged was unmistakable and unsettling. 3I Atlas was shedding material too rapidly, accelerating in brightness too quickly, and showing signs of internal pressure building toward an unknown breaking point. By mid-November, the quiet unease among astronomers shifted into open concern. Ground telescopes across Europe, Asia, and the Americas began reporting the same phenomenon, a rapid brightening that exceeded even the most aggressive predictions. Night after night, the magnitude readings climbed, transforming the comet from an obscure interstellar speck into a dynamic, shifting beacon in the sky. The ion tail, once modest and faint, stretched farther and farther, growing into a dramatic, blade-like structure pointing away from the sun. It pulsed with subtle variations, ripples triggered by solar wind, distortions that signaled a rising torrent of volatile material escaping from within. Stacked imaging from observatories revealed something even more telling. Inside the coma, the haze of dust began to show turbulence, small eddies and streaks moving in patterns too chaotic to ignore. Some frames captured a phenomenon observers called clumping, dense knots of brightness forming and dispersing in irregular intervals, as though something inside the nucleus was pushing outward unevenly. Public statements from astronomers grew more cautious, more measured. Many described the comet as behaving strangely, a phrase rarely used in formal reports. Yet it fit. No one saw outright fragmentation yet, no obvious break in the nucleus, but the instability was clear. Something was shifting beneath the dust, something that hinted at rising stresses. 3I Atlas was entering a new phase, one defined not by motion through the stars, but by a struggle within its own ancient structure. On the nights of November 23rd and 24th, the quiet mystery surrounding 3I Atlas broke open. The first signs arrived in amateur footage, captured through modest telescopes in backyards and small observatories. A sudden, unmistakable surge in brightness cut through the darkness, sharp, brief, and out of rhythm with the comet's earlier pattern. Those watching live described it as an explosion-like brightening, a flash that seemed to ripple through the coma. As the videos reached professional teams, analysts began stacking frames to understand what had happened. Slowly, as the noise fell away, something emerged. Multiple bright cores where only one had existed before. 2, possibly 3, each drifting with the faintest separation, as though the nucleus had been pulled apart from within. What had looked like a single object for months now resolved into separate components, each carrying part of the original body's light. Observers struggled to describe the scene. The coma showed clumping, dense knots of brightness pulled into new shapes. Structures shifted in minutes. Reports described rapid structural change, the kind rarely seen even in unstable comets. And as confirmation spread across networks and research channels, the tone among scientists shifted from curiosity to disquiet. The shock was not that 3I Atlas had fractured. Fragmentation is a known part of comet behavior. Weak ices crack, pressure builds, rotation tears structures apart. But what stunned the scientific community was the timing. Every projection had placed the risk of breakup weeks or even months further ahead. Instead, the nucleus gave way far earlier than anyone predicted. This early collapse carried consequences. Interstellar comets are extraordinarily rare. Each one provides a fleeting chance to study material forged around another star. A fragmentation reduces that chance, scattering the nucleus into smaller pieces that quickly fade or disintegrate. The scientific window narrows. Yet for all the uncertainty, one fact became clear during those 2 nights. 3I Atlas was changing faster than models could keep pace, claiming its place as one of the most unpredictable objects ever seen passing through our solar system. In the wake of the breakup, the central question sharpened into a single word: why? What force acted inside an object forged around another star, causing it to split far earlier than predicted? Scientists outlined several natural explanations, each grounded in established comet physics, yet each revealing a different facet of the mystery. The first hypothesis focused on rotational spin-up. Jets of gas do not erupt evenly. When one side vents more forcefully than the other, momentum builds. Over time, the nucleus can spin faster and faster until its structure fails. Light curve variations recorded before the fragmentation hinted at this possibility. A slow wobble turning into a dangerous acceleration. The second involved thermal stress. As 3I Atlas approached the sun, even at a great distance, heat began penetrating its surface. If its interior stored pockets of volatile ices, materials that vaporize easily, then sudden expansion might tear the nucleus apart. Many solar system comets have collapsed this way, especially when their internal layering is uneven. A third theory centered on internal pressure from volatile gases, especially CO2 or CO, trapped deep beneath the surface. If heat reached these reservoirs, they could release explosively, producing the kind of flash brightening captured in the first videos. The fourth explanation was structural. 3I Atlas might be a weak rubble pile, formed not as a solid block, but as a cluster of loosely bonded fragments. Such objects can fall apart under even modest stress, especially if they were assembled in a different stellar environment with different temperature cycles. Scientists also clarified what did not happen. There was no evidence of a collision with another object. The comet had not passed close enough to any planet to experience tidal forces strong enough to break it apart, and there was no credible scientific basis for any artificial or non-natural explanation. The observed behavior matched known physics, just accelerated far beyond expectation. What remained was a natural event, but one moving at unnatural speed. Even after days of analysis, the fragmentation left more questions than answers. The exact size of the nucleus remains uncertain. Early estimates suggested a small core, but the breakup complicates any measurement, leaving only indirect clues from brightness and dust production. Scientists also do not know how many fragments now exist. 2 or 3 bright components were identified, but smaller, fainter pieces may have separated as well, too dim to detect without deeper imaging. Another unknown is whether the fragments will survive perihelion. Some may disintegrate entirely as they approach the sun. Others may drift apart, fading until they become indistinguishable from background noise. The comet's volatile composition remains only partially understood. Hydrogen has been detected, but the proportions of CO2, CO, or other gases are still uncertain. Without precise spectroscopy, the internal structure remains invisible. 2 deeper mysteries linger: why the activity increased so sharply in November, and why the breakup occurred weeks earlier than predicted. Models built from solar system comets failed to anticipate the timing, suggesting 3I Atlas carries internal structures unlike anything commonly found in our neighborhood. In the quiet gaps between the data, these unanswered questions define the comet more than the answers we have.